Hello, and welcome to Astronomy Daily, the podcast that brings the cosmos down to Earth. I'm Avery, and as always, I'm here with the brilliant Anna.
Hello, Avery, and hello to all our listeners. We have a fascinating lineup today, covering everything from cosmic giants to microscopic survivors.
That's right. We'll be talking about a major confirmation of a Stephen Hawking theory, moss that survived the vacuum of space, a telescope on a balloon, a planet that's orbiting completely off-kilter, and we'll end by tackling one of the biggest questions out there. Is the universe infinite?
It's a packed episode. Shall we start with the giants?
Let's do it. Our first story is a big one. Two of the greatest minds in physics, Stephen Hawking and Albert Einstein, both had some of their most fundamental predictions confirmed by a single cosmic event.
This involves the collision of two black holes. Using gravitational wave observatories, scientists got their clearest observation yet of such a merger.
And the first big confirmation relates to Hawking's area theorem. He predicted that the surface area of a black hole, its event horizon, can never, ever shrink. It can only stay the same or grow.
Right. It's a law of black hole mechanics. And in this merger, they measured the surface area of the two original black holes and compared it to the new, larger one that formed.
And
the new surface area was indeed greater than the sum of the two initial ones. Hawking was right.
It's just incredible to see a theoretical prediction made decades ago proven so precisely. But that wasn't all they saw, was it?
No, it wasn't. The signal was so clear that they could observe the ring down of the new black hole. Think of it like striking a bell.
The ringing.
Exactly. The new black hole wobbled and settled into its final shape, sending out gravitational waves that faded over time, just like the sound of a bell. The specific frequencies and decay patterns of that ring down matched the predictions of Einstein's general theory of relativity perfectly.
So in one event, we get a check mark for Hawking and a check mark for Einstein. And this new object they observed is called a Kerr black hole, right?
That's correct. A Kerr black hole is one that is rotating. Since the two smaller black holes were spiraling around each other, the resulting merged black hole inherited that spin. It's the type of black hole we expect to be common in the universe.
Wow, what a powerful confirmation of our understanding of gravity and the universe. From the colossal to the very, very small. Our next story is almost the polar opposite.
It really is. This story comes from the International Space Station, but it's not about the astronauts inside. It's about something that was living on the outside.
On the outside, fully exposed to space.
Fully exposed. Scientists placed moss spores in a container on an external platform of the ISS. For 9 months, these spores endured the vacuum of space, extreme temperature swings, and the full force of cosmic radiation.
That sounds like a recipe for total destruction. I can't imagine anything surviving that.
That's what makes this so astonishing. When they brought the spores back to Earth, a high percentage of them were still able to germinate and grow.
No way. They just started growing again after 9 months in raw space?
As if nothing had happened. It speaks to the incredible resilience of life. Organisms like this, known as extremophiles, really push the boundaries of what we thought was possible.
This has huge implications for theories like panspermia, doesn't it? The idea that life could travel between planets on asteroids or comets.
It certainly makes it seem more plausible. If simple spores can survive the harshness of space for extended periods, it suggests that the building blocks of life might be tougher and more widespread than we ever imagined.
From survivors in space to a new way of seeing in space, our next story involves a very unusual observatory. We're not talking about a mountaintop or a satellite, but a telescope dangling from a giant balloon.
This is the Excalibur mission, and while a balloon might sound low-tech, it's actually an incredibly clever way to do astronomy.
It carries the telescope up to about 130,000 feet, which is above 99% of Earth's atmosphere. This gives it a much clearer view, especially for the kind of light it's designed to see, high-energy X-rays.
Mhm. X-rays that are blocked by our atmosphere. And Excalibur isn't just taking pictures. Its key function is to measure the polarization of these X-rays.
Can you break that down for us? What does measuring polarization actually tell you?
Think of light as a wave. Usually, those waves are oriented randomly. Polarization is like filtering the light so you only see waves oriented in a specific direction. For astronomers, the way X-rays are polarized tells them about the powerful and complex magnetic fields near their source.
So it's a way to map out invisible magnetic structures. And they pointed this thing at some pretty famous cosmic objects, right?
They did. The mission focused on two main targets: the Crab Nebula, which is the remnant of a supernova, and Cygnus X1, a famous system containing a black hole that's feeding off a companion star.
And by measuring the X-ray polarization, they are getting new insights into the physics of the neutron star powering the Crab Nebula and the geometry of the material swirling into the black hole in Cygnus X1. It's a whole new layer of information.
It really is. Balloon-based astronomy provides a fantastic, cost-effective way to get above the atmosphere and test new technologies. Okay, from new views to new mysteries, our next story presents a real puzzle.
Yeah, this one is a head-scratcher. Astronomers have found an exoplanet system named TOI 3884 where things just don't add up.
The planet itself is a super Neptune, larger than Neptune, but smaller than Saturn. It orbits its star quite closely. But that's not the strange part. The strangeness lies in its orbit.
It's wildly tilted. Most planets in a solar system form in a flat disk, so they tend to orbit in the same plane, aligned with the star's equator. This one is misaligned by about 62 degrees. It's orbiting on a crazy diagonal path.
Right. A 62-degree tilt is extreme. Usually, to get an orbit that tilted, you need a powerful gravitational nudge from another massive object in the system, like a giant planet farther out, or a companion star.
And the mystery is, there isn't one. Scientists have looked, and they can't find anything massive enough nearby to explain how this planet got knocked so far off kilter.
Precisely. The usual suspects are all missing. It leaves them with some unconventional theories. Perhaps the star's protoplanetary disk was tilted from the very beginning by a passing star early in its history. Or maybe there was another planet that knocked this one aside and then got ejected from the system entirely.
A cosmic hit and run.
Exactly.
And that theory of an ejected planet, a cosmic hit and run, why is that so difficult to prove?
Because the getaway car is long gone and completely invisible. A planet ejected from its solar system would become a rogue planet, drifting cold and dark through interstellar space. There's no star to light it up. So finding it, let alone tracing it back to its home system, is practically impossible with our current technology.
So scientists have a pretty big mystery on their hands.
Essentially. For now, it's an open case file. It's a reminder that planet formation is a chaotic and complex process, and our own solar system's neat alignment might be less common than we think.
Speaking of things being less common than we think, our final story tackles maybe the biggest astronomical question of all. Is the universe infinite?
It's a question that feels almost philosophical, but scientists are trying to answer it with actual measurements. The key lies in determining the overall shape or geometry of the universe.
And their best tool for that is the cosmic microwave background, or CMB. That's the leftover heat from the Big Bang, which fills all of space.
Correct. By studying the tiny temperature fluctuations in the CMB, cosmologists can measure the universe's geometry. There are three basic possibilities. It could be closed, like the surface of a sphere, open, like the surface of a saddle, or flat, like a sheet of paper.
And so far, every measurement we've made points to one answer.
flat. To within a very small margin of error, the universe appears to be geometrically flat. If the universe is truly flat, then in principle, it would extend infinitely in all directions.
Case closed then. The universe is infinite.
Not quite. Here's the catch. We are limited by our observable horizon. We can only see the part of the universe from which light has had time to reach us since the Big Bang.
The mind just reels at that. If it's truly infinite, that means that somewhere out there, an infinite distance away, there's another solar system exactly like ours, with another Earth and another you and I having this exact same conversation.
That's the logical, if unsettling, conclusion. With an infinite number of chances, any event with a non-zero probability must occur an infinite number of times. It pushes the boundaries of physics into the realm of philosophy.
Ah, okay, so it's like standing in Kansas. It looks perfectly flat as far as you can see, but you know that on a large enough scale, the Earth is curved.
That's a perfect analogy. The universe could be curved on a scale much, much larger than our observable horizon. It could be a steer or a saddle so vast that our little patch of it just looks flat.
And there's another wrinkle too, isn't there? The idea of topology.
Yes, even a flat universe might not be infinite. It could have a complex topology. For example, it could be shaped like a donut. If you travel in a straight line, you eventually end up back where you started. In that case, the universe would be flat, but finite.
Have scientists looked for evidence of that donut shape? For instance, by looking for repeating patterns in the cosmic microwave background, as if we were seeing the same region of space from different directions.
They have, very carefully. So far, no such repeating patterns have been found. While this doesn't rule out a finite universe, it does mean that if the universe is finite, it must be vastly larger than the part we can see. So, for all practical purposes, it might as well be infinite from our perspective.
So in the end, we're left without a definitive answer. Our measurements say flat, which points towards infinite, but we can't be sure.
Exactly. It's possible that because of the horizon problem, this is a question we may never be able to answer for certain. It's one of the profound limits of cosmology.
And what a profound place to end our journey today. From the laws of black holes to the hardiness of moss, from balloon telescopes to tilted worlds, and finally to the ultimate fate and size of the universe itself.
It really shows you the incredible range of questions that astronomy seeks to answer. Thank you all for joining us on this exploration.
That's all for this episode of Astronomy Daily. You can find us wherever you get your podcasts, and we'll be back next time with more news from across the universe. Until then, I'm Avery.
And I'm Anna. Keep looking up.